Alrighty, so now that you reviewed your types of triangles, right? Now let's actually apply them in a proof. So, start off by our mini proofs. So if you're given a piece of information, what can you conclude and why? So if you're told that triangle ABC is isosceles and that the base is segment AB, think about what that looks like. So if I draw the triangle ABC and I know that the base is AB, okay? By the definition of an isosceles triangle, we know that it has at least two congruent sides. So what we can, if this was my given, right, my next statement would be that segment AC is congruent to segment CB. And my reason would be the definition of isosceles triangle. Now let's look at this one. If triangle ABC is equal angular, right? So if we're given that a triangle is equal angular, you just reviewed what it means to be equal angular, right? So if a triangle is equal angular, it means all the angles are congruent, which is, people like to say sides. Angles, okay? So we would know that all three angles are congruent. So if my given was that the triangle is equal angular, the next statement would be that angle A is congruent to angle B, which is also congruent to angle C. And our reason is our definition of equiangular triangles. Alright, now here I'm told that triangle ABC is equilateral. By the definition of equilateral, that means that all the sides are congruent. So my next statement would be triangle or segment AB is congruent to segment BC, which is also congruent to segment AC. Draw yourself a sketch if you need it. This would be the definition, oh that's ugly, of equilateral triangles, okay? Make sure that if you're talking equilateral, you talk about sides. If you're talking about equiangular, you talk about angles. Until chapter 5 when we learn about the triangle inequality theorem. So now that you see how it's used with the given and the next statement, let's actually apply this within a proof, okay? So here's my proof. I have my figure set up and you're going to draw this all in your notebook, right? My proof statement is that B is the midpoint of segment AC. And if I look at my givens, I'm given that triangle DBC is isosceles and it tells me that the base is segment BD. And I also know that segment AB is congruent to segment DC. So as we always do, what we should, as we read the given, we should be marking our sketch, right? So if triangle DBC is isosceles and the base is BD, then that would tell me that my legs are congruent. Now, which legs are congruent? Well, and as you mark it, you should also write it. So that would tell me that segment DC is congruent to segment BC, and that's by definition of isosceles triangle. The other thing that I was given was that segment AB is congruent to segment DC. Now notice how I'm doing it in two different colors. So I can actually see that there is an overlap of a segment being talked about here. If AB is congruent to DC and segment DC is congruent to segment BC, then this is substitution, or as the book would call it, transitive property, but these then could cancel themselves out and we could conclude that segment AB is congruent to segment BC. And we're going to use substitution, although transitive property would be correct as well. Okay, but we stick with that universal substitution. Always keep the end in mind. The end in mind here is that B is the midpoint of AC. If B is the midpoint of AC, what would that mean? Meaning, like, what would we have to show to say it's the midpoint? Well, we would have to show that AB is congruent to BC, right? That's what it would mean if we could find the midpoint, if B was the midpoint. Well, look it, you already have that. You did it already. You're finished. This was a fast proof. So now we're finished, and we could say that B is the midpoint of segment AC. And why do we know that? That's by the definition of a midpoint. I love proofs. I especially love proofs when they end up like this. It's so much fun. When it's like, boom, you already had it and you didn't even know it. Yay. Good job. All right.